Can people see my slides okay?
Yep, we can see your slides.
So I'm going to talk about the U.S. Department of Energy's Hydrogen and Fuel Cell Technologies Office. So I work for this office as a senior analyst in the systems analysis subprogram. And this is really the core R&D technology support function for DOE for hydrogen and fuel cell technologies.
Hey, Mark, sorry, quick issue. I think your screen just went dark on your end. Yep, it was showing for a split second and then sort of disappeared. And now we can see it.
Okay, good. Thank you. So here's my opening slide, and I'm just going to show this slide here to emphasize that within the U.S. Department of Energy, there are several different offices involved in hydrogen research, R&D, technology commercialization. And just a few months ago, we published a joint program plan, which is the document on the left, which represents the combined effort of the U.S. Department of Energy on hydrogen technologies. Within that, you will see this diagram on the right, which is a little bit busy, and as typical for government, a lot of acronyms. I'm not going to explain this in detail, but I'll just point out that in the middle is the Hydrogen Program Management, which is the office I work in, Hydrogen and Fuel Cell Technologies Office. EERE here, can you see my cursor, Derek, if I do this?
Yeah, loud and clear.
Okay, so that's the energy efficiency and renewable energy, and we're really coordinating a lot of the hydrogen activities across these other offices. So I just want to highlight that to talk about which part of DOE I'm presenting information on, and to distinguish between some of the other research efforts for other programs within DOE. So one of the important initiatives in our office is called H2 at Scale, and the name recognizes really two different important themes. One is that the economics of hydrogen improves strongly with increased scale. And so that's why some of the projects that Zane covered are really exciting today, especially get up to gigawatt scale electrolysis units. The diagram on the left also shows the importance of scope, where hydrogen can be used in a lot of different end use applications. So this figure is showing the interaction between the electricity grid on the left and then different hydrogen opportunities on the right, where electrolysis is a link between the electric grid and hydrogen systems. So I think a lot of people have really heard about hydrogen use in transportation for fuel cell electric vehicles, but there are other uses of hydrogen. And as Zane pointed out in his opening comments, some of those are very hard to decarbonize. So having this link between reducing the carbon intensity of the electric grid and then being able to couple the hydrogen systems with the low carbon grid, we can then provide low carbon hydrogen to these other sectors that are difficult to decarbonize. So I'll point out that our program, it includes a lot of basic R&D, which DOE focuses on as technology research and development, but we also do some later stage commercialization efforts. On the right side of this graph, we show our total funding, which is $150 million per year, which is distributed across these 5 different activities: hydrogen production, infrastructure, which is really delivery of the hydrogen, storing hydrogen on board vehicles or off board, the fuel cells as an efficient way to use hydrogen, and then some integration across systems and commercialization efforts.
Hey, Mark, apologies to interrupt. Could you try to expand your PDF to be full screen, or would that black out the whole screen?
That's how it got blacked out last time. Is it hard to read?
I think some audience member is having a bit of issue reading.
Okay.
Yep.
Is that better?
I believe so, yes. And also, would you be possible to hide the sidebar on the right?
Right. How's that?
Thank you very much.
Thanks for pointing that out. So we heard about blue hydrogen before. So this is just a depiction of 3 general ways to make hydrogen. So carbon capture, utilization, and storage is an option for not just hydrogen, but for electricity generation, biofuels as a way to reduce carbon emissions. Biomass is also can be converted to hydrogen, as can basically any primary energy resource. And within the biomass, we would also include waste to energy processes. And then water splitting electrolysis is the main technology there, where we have the PEM and alkaline, but there are also some direct solar technologies that we've been funding for many years and are promising for as a long-term option. So one of the important things our office does is we prioritize R&D work based upon meeting certain targets. And this graph shows our cost targets. We also have technology targets in terms of efficiency and other technical parameters. But these are the costs for our fuel cell systems for light duty vehicles on the left, where the red is sort of the current status today, reducing down through our various levels of ambition into the future for reducing those costs. Part of that is achieved through economies of scale as the industry grows. Onboard storage, this is a generic target for all the different types of storage. High pressure tanks are really the main one used today. And then the figure on the right shows the cost at the pump. If you would drive your car up to a hydrogen station to refuel, we want to reduce that down eventually to $5 to $10 per kilogram, and the ultimate target being $4 per kilogram. So a lot of these targets are explained in the document I showed earlier, and if anybody's interested in learning more about the technology targets, I can send more information. This is an example of a hydrogen cost tool that we use to estimate the cost of hydrogen. The key assumptions are shown in the bottom. So this is electrolysis, with the cost of hydrogen just at production center being reduced from about $5, and just an example of what would have to happen to get below $2 per kilogram. A lot of other reports shown on the left here have found similar ranges. So these are some international organizations that have also estimated this cost range. And just quickly on the right, there's an important correlation between utilization, cost of electricity, and we're just highlighting there an area where we see the less than $2 per kilogram being viable. Of course, it's very complicated to go into the details of those, but just so people know that we have tools available that are very transparent and open to the public to do these types of calculations. So this is a busy graph. I'll go through it quickly. On the left, we're just highlighting sort of the status of commercialization today. We have over 500 megawatts of backup power for fuel cells. An important application here is for telecom, where the fuel cells have high reliability. So telecommunication towers are backed up with those systems. There's also an impressive number of forklifts operating in major warehouses around the country. So more than 35,000 forklifts that are running on hydrogen inside warehouses. So we also have PEM electrolysis units, fuel cell buses, hydrogen stations, where most of those are located in California, which is really the global success story for light duty vehicles for based upon the regulatory structure of California and supporting the growth of that new industry over time. And right now we have just over 9,000 vehicles on the road, most of them again in California. The graph in the middle just shows some of the production capacity, adds up to about 10 million metric tons, which is about 1/7 of the global total that Zane showed earlier. And then just to point out that we do have quite a few electrolysis units in place. A lot of these are supporting specialized industries, and you can see the sizes there going from 100 to 500 kilowatts. A couple more slides on the activities that we support. On the left, you can see we have over 1,000 patents that have been supported by our funding projects. About 35% of them come from the national laboratories. And then we also track how many of those have gone out to become commercial technologies that are in the private sector and no longer require government support. In the middle, it just shows some of the examples of some specific projects, specific companies that have been involved in these activities. And then we also support demonstrations, usually through cost share with industry, and those are listed on the right. There's quite a bit of material to document these. We really want to have demonstrations be a learning experience for other countries other companies that are interested in getting involved in this space. And I'll just highlight that one of the really exciting applications now, since we have supported light duty vehicles historically, and again, California is a success case there. But today there's been a lot of activity around heavy and medium duty vehicles, which includes large tractor trucks, buses, and smaller delivery trucks. So these are just some examples of projects that we've supported. In addition, there are opportunities in marine. So we have a hydrogen ferry project, which is shown on the left, which is in California, in the Bay Area. Stationary fuel cells for data centers, which require high reliability electricity supply, is shown in the middle. And then a very interesting opportunity to reduce carbon in the steel sector is to use hydrogen as a feedstock to reduce the amount of coal required to produce iron and steel. So that's a quick review of some of our projects, but I'll point out that if you move globally, and Zane touched on this and emphasized it, but the scale up of electrolysis units globally is really impressive. So this is just a visual to highlight that. And in addition, there have been waves of enthusiasm for hydrogen over the decades, and we are really in the middle of one now. Part of that is seen with roadmaps, strategy documents for different countries, different regions. A lot of those are shown on the left. Two important activities at the global scale are the Hydrogen Ministerial Global Action Agenda, which has this goal of 10-10-10, which is 10 million systems, 10,000 stations within the next 10 years. Another important organization is the Hydrogen Council, which is a private sector-led industry group. And it shows their projection there on the right of about a 10-fold increase of hydrogen generation by 2050, covering multiple sectors, not just transportation. A couple other examples of global collaboration is the IPHE, which now has over 20 countries. The US used to be the lead. The lead has been transferred over to the Netherlands with the US and Japan as vice chairs of that organization. And then in addition, we have a global collaboration on the Center for Hydrogen Safety, which is shown on the right. And I'll point out that we have a lot of different projects to try and support the commercialization of these technologies. This is a relatively new one to do workforce training. And if we see a fully fledged hydrogen system, there are a lot of different technologies that need support from a well-trained workforce. So this effort, about $20 million investment, University of Tennessee, is designed to address that need. So I just have a few more slides here. A really important meeting that we have for our office is every year we have an annual merit review. This year it'll be virtual. It's the week of June 7th. And at this meeting, we review a lot of our most important hydrogen projects where we have the lead people in each project present results and give updates. And that information is all posted online if people want to learn more. Also, we have a Hydrogen and Fuel Cell Day, which is on October 8th, which matches the periodic number for hydrogen for people who are studying their periodic tables. We also have a couple other outreach tools, information tools, H2IQ, and then H2 tools on the right. And these are websites you can use to access that information, those resources. We also have hydrogen fuel cell updates shown at the bottom there. For people involved in R&D or involved in partnerships with industry and government, these are some examples of some of our existing consortia on the left, some of our new consortia for different focus technologies, electrolysis and heavy-duty vehicles, and then some of our bridges between the national laboratories and industry, which we support through different funding mechanisms. And then on the far right, the private sector projects that we also try to support. So If you look these up, you can find more information. If you are unable to find that, please contact me and I can help connect you to the right resources. And that's my presentation. Thank you.